I'm going to get started. Hello? Yeah, so sorry I'm late. There was a car wreck on the, I guess the YOLO bypass is the technical term for it. But so 10 minutes less. Okay, great. We're going to talk about a topic that is really one of the cornerstones of image processing. It's called image segmentation. And it's a big enough topic that there's going to be 2 lectures dedicated to it, similar to how there were 2 lectures dedicated to object detection that we just went through. So today we're going to start with, you can already tell where this is going. Today's lecture is called Bottom-Up Image Segmentation. And on Wednesday we're going to talk about top-down segmentation. So it's really 2 different schools of thought as to how you solve this problem of image segmentation, which I'll define right now. Image segmentation is, generally speaking, the process of starting with an image, here a 4x4, some very overly simplified image, and grouping all of the pixels into coherent categories. By the way, I don't think I've used this word voxels yet, but when you have 3-dimensional volumetric medical images, such as are common in the later 3 weeks of the course, often a pixel is referred to as a voxel because each little element of the world that is taken up by a voxel is a little tiny itty-bitty volume. So they're volume pixels. But you can call them pixels too, and I won't care. You'll be just as right. So what we're going to do is take each of our pixels, aka voxels, and assign them to one of a small number of categories. So here I have made up 3 different categories, and I've assigned each one of my pixels to one of my 3 categories. So, obvious question that you start out with is, what do these categories represent? Well, this is where, vague, okay? Because different people have different senses of why pixels should get put into the same category, but the idea is that it's a low-level reason. All of the pixels in the same category have something in common. They belong together. They are similar. They hang together in some sense that is for you, the engineer, to decide. So all pixels in the same category belong together. So, like I said, this is one of the really cornerstone applications of image processing, both in kind of in all 3 areas, in 2-dimensional photography, in range data, radar data analysis, in volumetric data. And the reason why is that they're both direct applications of image segmentation, where once you assign pixels into categories, you're done with your work and you move on to some other job. And there's also, you can think of these as halfway points to solve some other problem. So in this sense, getting an image into categories, or segments is another term for categories, you want to do that as a stepping stone to get you to somewhere else. So here's some examples. In brain imaging, there are 3 basic different types of pixels inside the brain. Gray matter, which is something like the CPUs of the brain. White matter, which is something like the interconnect. And CSF, which is the soup that your brain is sitting in, that provides functions like removal of waste products and provision of nutrient. So you might want to know how much gray matter and white matter and CSF someone's brain has in it, period, and that's the thing that you're interested in doing. So that involves assigning every pixel in your brain image to one of 3 different categories. Similarly, in mammography, your risk of acquiring breast cancer goes up the more dense tissue is in your breast, and it's relative to the proportion of dense as opposed to fatty tissue that your breast is composed of. And similarly, in computed tomography, you might be interested in taking a CAT scan of the liver and assigning each of the pixels in the CAT scan to one of, say, 3 different categories: tumor, or liver, or background. then you can imagine why each one of those things is useful as an end in and of itself. Now, in other applications, like I said, we might want to use these categories or these segments of pixels for some other purpose. So you might want to first take your image of the brain, divide it into categories, and use each one of those categories to reason about whether or not someone has had a stroke or not. So for example, if you see a blot of spherical shaped blot of pixels that kind of looks like gray matter, and it looks like it's surrounded by a halo of, no, the other way around. So if it looks like a circular blot of white matter that is surrounded by a more or less spherical halo of gray matter, chances are you're wrong, and that's actually probably a stroke that is surrounded by blood. And neuroradiologists can use this kind of thinking about the categories and how they're arranged with each other to determine what's happened to someone's brain. Similarly, let's take another image domain like, how about remote sensing from an airplane mounted camera? So you have an airplane that is being flown by the military over Afghanistan, and what they want to do is build up a large extended map of the region that they are imaging. So the first thing that they might do is take a photograph and assign each pixel into segments that correspond to rocky terrain, forested terrain, and buildings. So then, if you want to align all of your images together and stitch them into one big map, then your problem has become simpler by looking at these segments or these categories, because basically pixels that are building in one image better line up well with pixels that are building in another image. So you align the buildings to the buildings, and the rocky terrain to the rocky terrain, and the forestry to the forestry. So again, segments or categories as being stepping stones to something further down the road. Now, I'd like to give recipes in this course, and so, and basically I'd like to kind of present to you, the engineer, what questions you have to answer, what design choices you have to make if you are going to solve said problem, and in this case, image segmentation. Because like I said, there's no free lunch, there's no problem that solves itself. You have to commit to some decisions no matter what image processing problem you are attacking. So this one you have to solve, or basically think about 3 different aspects to your problem. First of all, I've said that pixels that go into the same category are coherent in some sense. So you have to take that notion of coherent and define it. Say, why do I want to put pixels into the same category? What feature is it, or what interesting content of the image is it that's telling me to put a particular set of pixels into one category as opposed to another? The second thing, and this is a recurring theme again, how do you take your semantic notion of coherent and stuff it into mathematics? How do you make this thing mathematical or numerical? And in particular, the key thing that you're going to have to do is come up with a computational mechanism by which you can assign a similarity to a pair of pixels. So if you have 2 pixels, what you need to do is have a function that, for example, is close to 1 as its output if they're very similar to each other, and close to -1 if they're very dissimilar to each other, for example. And then you have to have some kind of mathematical model of what it means for categories of pixels to be coherent, and then you have to find solutions to those models. Once you define what coherent is in a mathematical sense, then you have to figure out how you're going to turn the crank to find a solution that assigns the same label to pixels that are similar to each other. Any questions? Okay, good. Shut up. So once again, we arrive at this slide that you have seen several times already, where at the lower left we have notions that are kind of crude, simple-minded, close to image pixel values. And on the upper right, we see higher level, more semantic notions. And this kind of schema applies to your notion of what it means for pixels to be coherent with each other, or to be in the same category. At one end of the scale, you can be very simple-minded and say, if 2 pixels are both red in terms of their color, they should be in the same category. If they're both green, they should be in the same category. So if they're the same color, they should be in the same category. Or if it's a grayscale image, basically you can say all the dark pixels ought to be in the same category and all the light pixels ought to be in another category. Making that more complicated, you can decide that pixels that are all plaid, in other words, they have coherent visual texture, ought to be in the plaid category, and all of the polka dot pixels ought to be in the polka dot category, and so on. That could be useful in a picture of a crowd where everyone's got clothing on. Similarly, lighting is often very, very complicated in terms of what parts of a scene are illuminated by what lights. And so you can decide, well, if two pixels are both illuminated by the same flash, they should be put in the same category. If you have a video, you can decide that pixels that move together should be grouped together. So if it looks like pixels are moving in the same way through a video, and we'll see an example of this in a minute, then they should go in the same category. And then when you get higher level here, you get to these kind of more not abstract, but more complex notions of what it means for pixels to be the same, which are not very closely tied to their pixel values in the image itself. Things like, well, if all of the liver pixels ought to be grouped together, all of the gray matter in the brain pixels ought to be grouped together. And these, being able to do this dependably is often left to human beings, and those human beings are often very, very highly trained, neuroradiologists in particular, and they're very, very highly paid. It's shockingly lucrative to be a radiologist these days. So that just gives you the sense that coherence can be defined along this spectrum from simple to complicated. And there are two kind of broad approaches in terms of how to codify what it means to belong in the same category. One is global, in which the mathematical entity of interest is basically a closed contour or a set of closed contours where each closed contour has a bunch of pixels in the middle of it, all of whom belong together. So you think about coherence in a global sense as a property that is defined by a big crowd of pixels. The opposite of that, as you can imagine, is that you codify mathematically what it means to be coherent just by thinking about the question of more or less a thumbs up, thumbs down decision about whether a pair of pixels are similar or not. Or, going back to what I just told you, a function that gives a high value if these two pixels belong together and a low value if they do not. And so the predominant approaches for image segmentation take one or the other of these two tacks, either of thinking about the entire group of pixels, the category of pixels as they belong together, or by thinking about pairs individually. Now, let's go through some examples of what people have done in developing methods for this problem in terms of how they define coherence. So, the thing you can do, like I said just a couple minutes ago, is that you can decide that pixels should be in the same category if they simply have the same color. And what's happened here, it's a little bit difficult to see, but the thing on the left is a photograph, and the thing on the right is the assignment of all of those pixels to one category or the other. So there's a brown category, there's a black category, kind of a turquoise one, a white one, and then two different green-colored ones. So you can see that this has not done a perfect job of interpreting the image the way that your brain has interpreted it in the course of, maybe a second, in which all of these pixels that are on the tree correspond to the same thing. They're all tree, right? So this hasn't done that. It's assigned some of the pixels to one category and some of the pixels to another. But again, this could be kind of a stepping stone application, where the next thing you do after you assign pixels to these categories is then do some other process that clumps these together into a tree based on their shape or how they're distributed in the image or something. But what you've done by going from the image to the left to the image on the right is basically dramatically reduced the amount of data that is present in the image. You basically reduced it to a set of, how many did I list off? 5 categories, I think, with the distribution of where those pixels are in the image. And this is the kind of result you can get if you just do the very simple thing of saying that pixels should be in the same category if they have similar colors. Here's an example of defining pairwise coherence in terms of visual texture. This is a kind of concocted image. This is not actually one photograph. But what it is someone took 5 different photographs of 5 different objects that all have different visual texture. So that's grass, that's wood, that I think is a sponge, that I'm not sure, and I'm not really sure about that one either. It's some kind of zoomed in photograph of some kind of material. And what they've done here is they've convolved the image with a set of Gabor wavelet filters, which we talked about a few times ago, which in some sense capture the frequency characteristics of little portions of the image at different orientations and different frequencies. And they say, well, if pixels have similar frequency characteristics in the sense of Gabor wavelets, then they should belong together. And if you do that, then you can get a segmentation of the image that does a pretty good job of identifying that all the pixels on the top belong together, all the pixels on this side belong together, and so on, by running a set, in this case, 3 different Gabor filters across the image and looking and reasoning about the outputs. So this is defining coherence within a category in terms of frequency characteristics, which are associated with visual texture. Now, this is a little bit more obscure here, because what we do when we think about this case is consider the idea that, simply stated, pixels should be in the same category if they're on the same side of boundaries. If they're on opposite sides of a boundary, they shouldn't be in the same category. So what you do is you first detect edges in the image using, for example, a canny edge detector, which we talked about in the second week. And then you say, well, these 2 red pixels should belong together because there's no boundary in the image that is between them. Similarly, the red and the blue pixels should be in different categories because they're on opposite sides of the image. So this is what's called a metric space, because you're not extracting some property from the red pixel, like color or visual texture or lighting or material properties or anything else, and extracting that same property from the blue pixels and comparing that property. No, you're simply just stating whether or not they should be in the category based on a pairwise relationship between them. So this is another sense in which pixels can belong together or not. This is the motion example. So what we have here is a video stream of, it's kind of like one of those helicopter-mounted video cameras following someone who's fleeing the cops on the 6 o'clock news, O.J. Simpson type thing. And what has been done here is we say, well, look, what we're going to do is estimate the motion of every pixel from the first frame of the video to the second frame of the video. So we're going to come up with a story for each pixel about where it has gone between the first frame and the second frame. So I'm going to say this first pixel here has gone from here to here in the first frame, from the first frame to the second frame. And if you do that, then what you can do is say, well, like I said earlier, pixels that move together, or pixels that move in a similar way from frame to frame, should get grouped together into the same category. And if you do that, you get the result on the right, where all the green stuff, all the pixels in the green category are grouped together, and all the pixels in the brown category are grouped together. And simply stated, basically, it looks like all the green pixels are moving that way, and all the brown pixels are actually not going anywhere, really. They're kind of just staying in the middle. Question? Microphone?
Does every pixel have to have a vector? Because it looks like some pixels are going to get lost or occluded. So which way do they move then? What's the result?
Right, that's a good question. And it has to do with how you estimate this motion from frame 1 to frame 2. There are all kind of ambiguities in estimating the motion. And hopefully you'll see where it goes. Oh, no. Yeah, well, it's too fast. But when the stoplight or whatever it is runs past this way, then the motion of all the pixels that are in the brown category but are next to the stoplight gets lost. because that pixel is occluded in the next photograph. So really the right thing to do is to say, I don't know. But usually what actually happens in practice is that you get a wrong answer. And the way that algorithms like this get around that wrong answer, and probably what will actually happen is that it'll say that the motion is in that direction or that direction because it seems to be the best answer you can come up with. But usually what happens in these kinds of approaches is that there's so many other pixels around it that are giving you a right answer. So for example, the entire bed of the truck might be doing the right thing, and it's just this stuff right here that's going wrong, that they kind of outvote those wrong pixels and they smooth over them. Any other questions about this example? Here's another one, and the same thing as Carl Lewis. A few frames of him running. And again, we have the idea that pixels that move together should get put in the same category. So it's not hard to see that the entire crowd is moving to the left. Carl not really moving that much at all, but part of his arm is moving down and part of that arm is moving up. But mostly what's happening is that he's just sitting still. Now, does anyone have any thoughts as to why his forward shin, or let's see, actually no, that's his back leg, is in a different category than the rest of his body? Yes, it seems to be that his whole body is moving in this direction and his kick leg back there is doing the opposite thing of going up as opposed to going this way. And really what I probably would have done if I was this algorithm is probably put his other leg in a different category too. Yeah?
Is it just from one frame to the next, or is it kind of global?
It used to be that it was too computationally expensive to do global estimation of motion. And usually what people would do is do frame-to-frame motion estimation, and then after the fact try to seam those, tie them together. But now it's becoming more and more common to do that kind of global motion estimation. Usually no more than 3 frames, though, actually, just because it's computationally expensive. Okay, now let's go on to a further notion of coherence, which has to do with depth. So I've told you a couple of times that if you take 2 photographs of the same scene from a slightly different point of view, just like your eyes do, you can then identify correspondences between the image from your left eye and the image from your right eye, and then triangulate to figure out how far away things are. So then, if you can do that, then it's an obvious notion that you should group pixels together if they have similar depth away from the camera. Or that pixels in the world should group together if they are at similar depths, which seems to have the connotation that they're the same object. And that's what's done here, where every different brightness here corresponds to a different depth away from the camera. So again, we're just going over a kind of a laundry list of different ways that different engineers over time have codified this notion of being in a group of pixels that belongs together. Now, once you have, actually I'm going to pause there and I'm going to do a couple of announcements. And what you're going to see is the announcements being done live. So for one thing, office hours are canceled this week. Sorry for the last minute notice. Something came up at the last minute. I just can't do it this week. I'm going to put up a sign on the door too. There's a chat room on SmartSite now. Let me or Jing know if you would be interested in chat room office hours. So the last time I offered this course, I sat in my office in this SmartSite chat room during a couple of hours, like the day before the homework assignment was due, or the day before the midterm, or the day before the final. Nobody was interested. I think I got one person who asked me one question. So I didn't bring that up as a possibility this time for that reason, but I was asked by one student if this was a possibility, so let one or the other of us know if this is the kind of thing that you're into, and we can do it, because it's really easy to do, actually. There's also a forum on SmartSite for posting your questions about the course. And I'm not sure if I can set it up so that I get an emailed notification telling me that somebody has posted something to the forum, but I hope so, because I want to be able to respond in a timely way. Anyone have any administrative type questions? Great. Okay, so no office hours, chat room, forum, lovely. Okay, sorry, I did that in the wrong order. Now, as I said, once you come up with your notion of what it means for two pixels to hang together, or for a group of pixels to hang together, you then have to squish that thing into a mathematical model. And previous approaches to image segmentation have taken one of 4 different approaches, which I probably won't have time to go through each one of them, but they are, I think, okay described in the slides. And we'll go through each one of these. You can think of your pixels in different kind of abstract mathematical senses, either as clusters in a high-dimensional space, which a concept we are familiar with, as a fully connected graph, which I don't think we've talked about, as a 2D lattice, and as a set of regions, which I a little bit alluded to earlier. Now, so let's start with clusters. So this one it should be easy for you guys. So what we do is, just like in the case of finding matches between rectangular patches of pixels in one image and rectangular patches of pixels in another, we can simply extract a vector of features, v1, v2, vk, using some feature function that encapsulates our idea of coherence, that assigns colors to things or texture descriptions to things using Gabor filters, for example. And then all you do with these feature vectors that correspond to each pixel is that you then cluster those things. And simply put, clustering is a general problem that is all over the place in data mining and machine learning. And so what people have literally done in the past is converted each one of their pixels into a feature vector and run a standard clustering algorithm from data mining on them to assign them into categories. And again, I'd refer you to the data mining or machine learning courses for more information on how exactly one does this. But there are some gotcha questions that you need to answer. One of them is, how many clusters should there be? So unless you have a preconceived notion that there should be 3 categories total, white matter, gray matter, and CSF, if you just say, oh, there's some number of categories, group them together, please, then that's a problem for a lot of different clustering methods. What features should you use to encapsulate your notion of coherence? That's an obvious design choice for you. How you decide what the distance is between pairs of feature vectors. So basically what you're going to do is that if this pixel here corresponds to that feature vector, and this one corresponds to that feature vector, you have to assign some distance in between them. So to determine what parts of the feature vector are important for defining how far they are apart from each other in this feature space. And also, what are the shape of these clusters? If you imagine a high-dimensional feature space, in this case 2-dimensional, then each one of your categories is going to carve out some subspace of that space, and that subspace has some shape to it. So you have to basically make a design choice about what the shape of that thing is going to be. Here are just some example results. Basically, the first one I showed you with color was one of these clustering-based approaches. Here's another one where it's the same kind of representation. And as you can see, it's done a pretty good job of putting the background into one category, the hand into another category, and the teether toy, I think that's a teether toy for a little baby, into a different category altogether. And because it has decided that there should only be 3 categories. So the ring, which looks different, is not put into its own category. So that's, again, one of the kind of little gotchas of clustering methods. Here's another set of results, which I think is fairly straightforward. The bottom one is a medical application where the thing you're looking at, the darker, lower pink thing is a blood vessel. And so we're segmenting an image of that. Now let's get back to this idea of metric spaces. So again, in metric spaces, the thing that you have is not a set of properties or a set of features for this pixel and a set of properties or a set of features for this pixel and so on. All you have is a set of pairwise distances. All you have are a set of relationships between pairs of pixels. And again, what you can do is come up with some way of putting this into numerics, of saying basically two pixels that are on the same side of the boundary have a low distance between them or a high similarity, and pixels that are on opposite sides of the boundary have a large distance between them. In other words, have low similarity. So what you can do is represent your entire image as a weighted graph. So everyone knows what a graph is, right? It's basically a set of nodes, which are these black dots, and a set of edges between nodes. Now I can't draw all possible edges between all possible pairs of nodes, but because it would just be a mess, but trust me that they're all there. And what you're going to do is assign a number to each one of these edges that corresponds to that similarity. So if two pixels are similar to each other, like these two, the weight between them is going to be large, or the similarity between them is large, so the weight of this thing is going to be large. And conversely, if two pixels are on the opposite sides of a boundary, then the weight between them is going to be low. Ooh, gosh. Let me fast forward for a second. Right. Yes. So the weight between the dissimilar pixels is going to be low. So you might think about this in maybe a transportation type of analogy where the road between two cities that's not very tightly connected to each other is a very thin road, and so the connection between those two cities is not very strong. Meanwhile, this has a 6-lane freeway between it, for example. Or you can also think of other kind of structural analogies, especially from computational chemistry, for example, where there are tight bonds between molecules and weak bonds between molecules. You get the idea anyway. So then, what we do is we formulate the problem of image segmentation, in this case into two categories of pixels, as the problem of finding a cut through the graph. And cut means what you think it means. It means that you're really doing something like taking a pair of scissors and cutting through a set of these edges so that, in the end, you can rip the nodes apart into one disconnected group of nodes over here and another disconnected group of nodes over here. And while I'm doing this cutting, the thing that I'm trying to do is cut through the weak links and not cut through the strong links. That's why it's called a minimum cut. The idea is that if you add up the strengths or the weights of each one of the edges that you cut through, that's minimized. So the sum of the weights in the so-called cut set, which is the set of links that you cut through, that should be minimized. And I don't know why I'm so big on analogies today, but you can imagine that if the strong links are like thicker metal and you're cutting through them with shears, the min cut, dulls your shears the least. You're cutting through all the weak stuff and not through all the strong stuff. It has been shown that finding the cut set for any given graph, a general graph, that minimizes the cut, that minimizes the sum of weights of the cut set, is NP hard, which means don't try it. It's going to take, in the extreme where you have a data set that is any size that is interesting, you'll spend forever doing it. And furthermore, a typical minimum cut, a cut set that minimizes the sum of weights of the cut set, a typical one looks like this. So simply put, you have one segment or one group of pixels that is the entire image minus 1, and then you got the 1 that's all by itself. So there's no notion that the two groups of pixels should both be, I don't know, somewhat large or non-trivial in this sense. And therefore, finding the minimum cut for image segmentation tends to be non-useful in practice. Now, what the normalized cut does, and I'm only going to spend a minute on this, I'll let you look at the formula after the class, but what the normalized cut tries to do is what it sounds like it does. It normalizes the weight of the cut set by how large each of the segments are. And so, and it takes a minute to figure out why that formula does it, but you can just think about it as penalizing that situation where one of the segments of pixels has very low weights going from itself to everyone else. And basically that the size of each of the segments should be relatively large. And it turns out that if you relax this problem, in other words, try to come up with a numerical solution to it, it turns into an efficient normalized eigenvalue problem. And this was shown in a seminal paper by these two guys, John Boshi and Jitendra Malik at UC Berkeley. And it's one of the kind of classic papers in image processing. So a lot of people do normalized cut for image segmentation for this reason, that it can be solved efficiently. Here's some results. That's a spinal column. You can see the vertebrae that are being segmented away from the background into two different categories. And the features here are what's called intensity histograms, which I won't really get into. Here are some other normalized cut results. And the top image, it seems to do a somewhat reasonable thing of putting the two players into two different categories. And this is kind of an odd one, but the other categories I think are somewhat reasonable. And the main criticism of normalized cut is that if you tell it to break up the image into too many categories or not enough categories, it kind of goes haywire. I'll skip over that. Now, instead of encoding relationships between all possible pairs of pixels, as I've said in that previous graph that I was talking about, every pair of pixels had a connection between it that you could or could not decide to cut. Instead, what we can do is just encode relationships between neighboring pairs of pixels and use these relationships to assign labels to every pixel. Now, we talked about Markov random fields already a little bit. And Markov random fields are one thing that you can do to encode these relationships between pairs of pixels. And what I told you is this somewhat amazing fact that for Markov random fields, all you need to do is define what's called a compatibility function that decides how compatible two different labels at two different neighboring sites are for each other, and an observation function that relates the imaging data to any individual label. And what emerges from that is a global kind of behavior. Is a predictable global distribution over the set of possible labelings that are in some sense implied by the imaging data. And what I also told you is that there's a whole literature on how to efficiently assign labels to images that try to maximize the compatibilities between pairs of pixels and assign labels that obey the observation function. And it's a set of computer programs called Markov random field solvers. So we talked about that already. You specify a lattice over the image, you specify your compatibility function and observation function, and you fire up your favorite Markov random field solver. And you're done. And I showed these results already, actually. I think I'm going to stop here because the part about the other way to do it is to formalize everything, not in terms of pairwise relationships between pixels, but between over entire regions. And you can basically come up with a set of ways of determining where these global regions ought to be, which you can go over on your own time. Any last minute questions about image segmentation? Bottom up, I mean.
And what are the two functions again for markups?
Go microphone.
Okay, sorry. I just realized I can look again on the slides for the two markup functions.
I can just quickly say them over again. Compatibility, which is between pairs of pixels, an observation function that relates labels to imaging data. All right. Thank you.